So far, so good? Mm-hmm. Now we're going to talk about graph intervals of concavity. Now let me just refresh your memory on concavity real quick. Remember when you can hold your hand up like this and water holds it?
Cup is up.
Cup is up, concave up, and if the water would fall out, it's concave down. Okay? So, again, we're going to look at it from our negative infinity to 0 and from 0 to positive infinity, and we want to see what's going on here. On this first one, if you kind of look at this here, it's kind of curved this way. Mm-hmm. Are you seeing that?
Yeah.
That's going to be concave down. Is that making sense?
Yes.
Mm-hmm. And this one, can you see, even though it only starts here, it still has the curve going up like that?
Mm-hmm. Yeah.
So that's going to be concave up.
Okay.
So for our interval of concave upwards, what is that going to be from?
Negative
No, look carefully. The upwards.
0 to infinity.
0 to infinity. Yes. Okay. Are you seeing where I'm finding that? Mm-hmm. And then concave downwards, where is that?
Negative infinity.
Negative infinity 0.
Correct. Now notice we're not putting, these aren't points, these are intervals. This is saying from 0 all the way to positive infinity, this baby is concave upward. This is saying from negative infinity all the way up to 0, it's concave downward.
So
now,
why do we write it like that then? Why don't we do
this is just called interval notation.
Okay.
Another way would be 0 is less than x is less than infinity. Okay, it's the same type of thing, only mathematicians, instead of doing the less than compound stuff, they just do intervals like this.
Okay.
Alrighty? See over where it says points of inflection?
Mm-hmm.
A point of inflection is where a graph changes concavity. So where would that be on this graph?
0, 0.
Exactly. So point of inflection on this one would be at 0, 0. Now that is a huge deal in a lot of things. Like, for instance, we have these normal distribution curves we're looking at. And when it goes from being concave down and changes to being concave up is somewhere in there. Mm-hmm. And being able to find that point is like a little thing that you do with calculus, which is really cool. Okay, but I have a program that will help you. If you label from, somewhere here to somewhere here, it will find that point for you, your point of inflection on the graph. And if you remind me, I'll get it to you on the calculator. I'll have to upload it, but then I'll take it and load it down to yours. Okay, but this is a big idea for further and further and further. Okay, and it's very important when you start looking at these. Like this is
the fifth.
Yeah, let's see, 1, 2, 3, 4, 5. Yeah, fifth degree equation, right? Mm-hmm. So we got some concave down going here, right? But then here it's going to change to concave up. Mm-hmm. And somewhere in here it's going to change back to concave down. Somewhere here it's going to go back to up, and it's going to stay up. Right? Mm-hmm. So you can have more than one point of inflection, depending on the graph.
Yeah.
Good to go on that one? Mm-hmm. On the cubic, we just have the one. Okay? And now we're going to talk end behavior. And we did look at end behavior just briefly the other day. Remember that? Mm-hmm. Okay, so let me just redraw my graph real quick. A horrible representation. All right. It says as x approaches negative infinity, y approaches what? So let's
Negative infinity.
It's going to go back this way. So where's my y going?
For negative infinity.
Oh, towards negative infinity, right?
Mm-hmm.
Okay. All right. So and then it says as x approaches positive infinity, what is y approaching? So as I go towards positive infinity on x, where's my y doing?
Positive infinity.
Exactly. Now, if you remember right, x cubed, is that odd or even?
Odd.
Odd. It's an odd function. And my leading coefficient here is just a 1, so that's a positive, right? And remember, if you were looking at just a line, y equals x, that's also an odd one. And when you draw y equals x, it just looks like this. So remember, with an odd function, it starts low and ends high. Starts low, ends high. Okay? I'm going to give you a couple of alternate forms and some locator points, and we'll be done with this one. Alternate forms of the equation look like this. Y minus k equals a times x minus h quantity cubed. The way we've been doing it would be y equals a times x minus h quantity cubed plus k. This would be the calculator one. Okay. So instead of calling that the
point slope. it'd be
vertex form of a
something else.
quadratic. It's just
Right.
a cubic type thing, but it's a perfect cube. Okay. Let's see. The other one that you'll see more often would be y equals ax cubed plus bx squared plus cx plus d. Okay. And what they do is a is always considered your leading coefficient. All right. And then they just do it alphabetically. Boom, 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 boom. Okay. So earlier, when we were doing y equals mx plus b, we would do ax plus b. In some European countries, they do that. They don't even consider m. They don't say m as slope. They just go with a because they deal with the leading coefficient business. And it just keeps everything similar instead of giving it a different name.
Yeah.
And it's not always 0 comma c that is your constant. It's whatever's last. In this case, or not yes, constant. In this case, your constant would be d. So your y-intercept would be at 0 comma d. Does that make sense as we go along there? All right, locator points. One of the most important points on this whole graph is at 0, 0. It is your inflection point. So you probably want to write that inflection point, even though it's already down there below. This, I would put these locator points. It's right below your graph there. And then if you have the form y equals parenthesis x minus h, a times x minus h quantity cubed plus k, then your locator point there would be hk.
Would 0 comma d be a locator point?
No,
Okay.
no.
And also, is there like something like the intercept form for cubic?
There is, it would be y equals a, but we don't normally use it. X minus p, x minus q, x minus r. That would probably do it. This would tell you the zeros where it crosses, right? So this is just written as a perfect cubed. Whereas when we were doing the other, we completed the square, rewrote the vertex form as a perfect square. But as you can see, there's no vertex on your cubic graph like there is on the quadratic. So it's not quite the same thing. We certainly wouldn't call this vertex form. Okay, perfect cube form, maybe. Learning how to write it as perfect cubed. Are we good? I guess this would be one where it would only cross once. It wouldn't cross multiple times. It would always have to cross at only one point.
Yeah.
Right? Because if you solved x minus h, all your x's would be equal to h. Right? So it's only going to cross at h comma 0. Are we okay with that? All right, so that's going to do that one. We won't do quartic today, so kill that.